everyone. Thanks for being here. It's my pleasure to introduce Simone Lizotte, who's visiting here from Quebec. Simone did his bachelor's and master's at the University of Laval. He's now going for the trifecta as a PhD student.
Exactly.
Simone works on network science and Bayesian inference at intersection, and more recently a strong focus on network geometry. It's a really cool combination of things. It's great to have you here this week. So looking forward to it.
Great. Thanks a lot, Eric. So today I want to talk about this recent project we did where we used Bayesian inference to infer the embedding of networks in hyperbolic space. And so since network geometry and Bayesian inference are usually not mixed together, I think it's important today to give you some context. So I'm going to introduce a lot of things so everyone can follow easier. So first, one of the most important thing in network geometry is that the principle that creating an edge requires a cost. And for instance, in a transportation network, this can be fuel, or in a brain network, this can be energy, or it could be material cost and power grid lines, right? And so what we do is that in network geometry, we represent vertices as being points in a metric space. And we assume that the cost increases with the length. And to do this, we assume that the edge probability is a decreasing function of the distance. And so this set of coordinates for the vertices is what we call the embedding. And this embedding can be useful in the various applications. It's used a lot in machine learning. For example, you could use that to find out how similar are different words in text. And this metric space can be physical. For example, in transportation networks, we can place the vertices on the surface of the Earth. But in this talk and in many other applications, we can also think of this metric space as just an abstract space where we put things and use the distance there. So in this talk, in this project, we're going to be using the hyperbolic space. So what is the hyperbolic space? Well, it is a connected Riemannian manifold of constant negative curvature. And without going too much into the technical details, connected means that there are no holes. Riemannian means that there is some kind of smooth structure, and you can perform calculus on the manifold. And the curvature, I think one way to see it is looking at surfaces. So here we have three surfaces of constant curvatures. So on the left, we have the pseudosphere, which has a negative curvature. We have on the middle, we have our beloved Euclidean space, which has a zero curvature. And on the right, we have the sphere, which has a positive curvature. And what we can see is that if we draw the shortest paths in these spaces, they are curved when the space is curved. So this is kind of what is unintuitive about these non-Euclidean geometries. But one important fact about these spaces is that the area of a disk, so if we draw a ball of a given radius, the area of that disk does not grow the same way in these different spaces. So we know that in Euclidean space, the area of a disk is pi times the radius squared, right? But it turns out that when we have positive curvature, the area of that disk is smaller. And when we have a negative curvature, the area of this disk is larger. And what is a little annoying about hyperbolic space is that we cannot view it properly in our 3D Euclidean space. And so this is different from the Euclidean and elliptic geometries, where we can, for instance, have a sphere, elliptic geometry, or we can have a plane for Euclidean space that we can view in 3D. But for hyperbolic space, what I showed you in the previous slide has a finite surface area. So it's not the complete hyperbolic space, which is infinite. So we're stuck using what we call the local coordinates. And in this representation, the straight lines are not the shortest paths. And that is a little bit hard to think about. And the coordinates we're going to be using in this presentation are what we call the polar coordinates. So we have two coordinates, as for the polar coordinate for the Euclidean plane. We have the radius, which is the distance to the origin, and we have the angle with respect to some arbitrary line. And what we can see is here the shortest paths, which are in purple, are curved. And so in this model we're going to be using, we're going to place vertices in that hyperbolic space, and we're going to restrict the vertices to be in a disk of radius capital R. So with that in mind, we can define our H2 model, so the hyperbolic model of a graph, where here we have that the probability that an edge exists decreases with the distance. So we here have the hyperbolic distance, obviously, but the sigmoid also depends on two other parameters. We have the beta, which controls the sharpness of the decrease in the sigmoid, and turns out it also controls the clustering in the graph. And we also have the capital R again, and this controls the half height of the sigmoid. Now, it turns out that this model we can represent using the circle, which may seem a little weird because we go from a hyperbolic plane, which has two coordinates, to a circle, which has one coordinate. But in that case here, using an approximation, we can see that the connection probability is now depends on the distance on the circle. And what was the radius is now the kappas. And the kappas are sort of a rescaling of the radial part of the hyperbolic space. And it essentially is the expected degree of the vertex in the model. So I think of the S1 model as a more intuitive model to the H2 model, where it's kind of a rescaling of the radial part, and we can see that as the average degree. Now, so why do we use these models in the first place? Well, the reason is when we generate graphs using these models, we have various properties that emerge from this geometry and properties that we observe in empirical graphs. So first, we have a high clustering. We have some community structure to it. And if we place the vertices uniformly in our hyperbolic disk, we obtain a power law degree distribution with exponent free, which is pretty interesting. And also, I think one of the most intriguing property of this model is that the shortest paths in the hyperbolic space are similar to the shortest paths in the graph. And what this allows us to do is something called greedy routing, where usually when we try to find the shortest paths in the graph between two vertices, we have to do some kind of algorithm and go through all of the possible paths we can take. But what we can do when we have positions for our vertices, for example, here, if the vertices are on the plane on the screen, well, we can follow the closest neighbor to the destination. So the neighbor which has the smallest distance with the destination. And what we can see is that, for example, in that case, if we do this successively, we get the optimal path between the two vertices. And it turns out that when we use hyperbolic geometry, this works really well, which is not a given because we can get cycles and we may not reach our destination with that algorithm. But what if we want to do these applications, but on a real network where we do not know the position of the vertices? Well, for that, what we want to do is represent that graph using the hyperbolic space. So for that, what we want to do is position the vertices in that hyperbolic space such that the model generates the graph with high probability. And in essence, what this means is that we want to place pairs of vertices that are connected in a graph. We want to put them close together. And pairs of vertices that are not connected, we want to push them apart. Now, to do this in a principled manner, what we actually do is write a likelihood for this graph. So this is simply the probability over all the edges. And what we try to do is maximize this thing. And so this is what many algorithms right now are doing. And it gives us the maximum likelihood estimator. And it turns out this is really challenging because there are a lot of local maxima in this model. So here in this figure, I plot the log likelihood for different values, different positions of the same vertex. So essentially, I fix an embedding. I pick one vertex, I move it around the circle, and I look at the values of likelihood. And we can see that there are some dips in the likelihood, and these create local maxima. And furthermore, these dips are discontinuous in the gradient, so it makes optimizing even more hard. So nevertheless, turns out that the algorithms that exist work pretty well. but there is still an issue with them, and it's that they give a single embedding. So I said earlier that we want to find the embedding that maximizes the probability, but this does not tell us if there exists other embeddings that are also good. So are there more than one plausible embedding? And it does not tell us how precise our embedding is. Is there some leeway? Can we move a little bit the vertices around? And so to answer these questions, in this project, we use a Bayesian approach. And so before going to this model, I want to take a few steps back and explain why Bayesian inference solves our problems here. So Bayesian inference is essentially a method that learns parameters of a model, here lambda, from some data x. And in Bayesian inference, we have three very important quantities. We have first the likelihood, which is essentially our model. It's how we believe the data was generated. And this model, for example, can be a normal distribution where we have two parameters. We have the average and we have the standard deviation. And so these would be the lambda. And then in Bayesian inference, we also have a prior, which defines how likely each value of parameter is. And this is before measuring the data. So it's essentially encoding our beliefs about the values of parameters in our model or in our data set. And finally, what Bayesian inference does is it mixes the hypothesis about the values of lambda with the actual likelihood, and it gives us the posterior distribution. And this is kind of an educated guess about what the values of lambda should be, given the data we observe. So I think the best way to see how it works is look at a very simple example. So here we have the classical example of statistics where we toss a coin n times. We suppose each toss is independent. And we have the following likelihood, which you've probably seen a million times. But the Bayesian part here is we're going to assume, for example, that each value of the probability row is equally likely. So we have a constant density for our prior. And in that case, we have that the posterior distribution is proportional to the likelihood. And we can work out the maths and figure out what is the normalization constant for that and figure out the distribution. And if we do all of that, and here we suppose that our data is that 4 throws out of 10 are 1, we get the following posterior in purple. So what we can see here, first we can see the prior, which is in orange here. So we believe that each value of lambda, or here rho, is equally likely. But when we introduce our data, so our posterior distribution tells us that the parameter of this model should be around 0.4. And this makes sense looking at the data. And that's what we would get if we were to maximize the likelihood. But what Bayesian inference does for us is that it gives us a distribution. So we get an idea of what's the uncertainty about this parameter. And it also would give us, if there's multiple values possible, we get a multimodal distribution. And so also one thing that it is interesting is if we were to have more data, it would peak more. The uncertainty about the value would be smaller. So this is a very simple model for which we can compute the posterior distribution analytically. But in most cases, we cannot do that, well, easily. And so what we do in general is instead sample this distribution, because we have to compute integrals to extract information from the posterior. And it's much easier to do that using numerical samples. And so what we usually use for that is what we call the Metropolis-Hastings algorithm, where we want to sample from a density. And so for that, we have an expression of this density without the normalization. Then we pick an initial state. And at each iteration, so here I'm going to show you. So, okay, I'm going to try to click on that, which is very small. Oh, that's unfortunate. Okay, I'm going to just scroll. So at each state, we have here we have the state in purple. And at each iteration, we have a proposal distribution, which here is in black. And it tells us where we want to go next. So this is a random walk. So at each iteration, we propose a new state. and we might accept it with a certain probability, which depends on our density we want to sample. So here the point is in green because we accept it, but sometimes we might refuse it. Like here, it's in the red, sorry, and we refuse it. And so if we can keep going like this, and if we look at the end, we can see that the distribution here, which is bimodal, which we want to sample, it like the histogram of the positions of our Markov chain resemble our distribution. And if we run this algorithm long enough, we're going to get the correct distribution. So this is a very useful way to sample our posterior distribution. Okay, now going back to our Bayesian model, what we want to do is define a Bayesian model for the S1 model. And so to do that, we already have the likelihood. This is the likelihood of the geometric graph. But now what we add to this to obtain a Bayesian model is priors on the parameters. So we want first a prior on the beta parameter, which is the sharpness of the sigmoid. Then we have a prior for each vertex, which here is a uniform distribution because we don't really know where the vertices should be. And then so the prior for beta, I forget to tell, is a normal distribution in our case. And for the kappas, which are the expected degrees, we use a Cauchy distribution. And this is because we want to have a heavy tail. And while we could have used a power law here, but we saw that in practice it didn't work as well as the Cauchy distribution. And so now with that, what we want to do is sample that posterior and obtain a sample of the best embeddings we can get for that graph. And so to check if that works, what we want to do is first choose an embedding. We're going to generate a graph synthetically from this embedding. And then we're going to forget what this embedding is, but we're going to try to recover it using our method. And so what we see when we try to run this with the usual sampling algorithms is that it does not work really well. So here we tried Hamiltonian Monte Carlo, which is a kind of sophisticated metropolis Hastings. And we also try a usual random walk, like I showed earlier. And so what we see is that if we initialize, so the first state in the metropolis Hastings, if this is the ground truth of the model, which we know because it's a synthetic graph, we can see that we get a certain oscillations of the log likelihood, which is expected. But we can see that both samplers are not doing the same thing, which is kind of dubious. And also, when we initialize it randomly, which is what we have to do because usually we don't know what the ground truth is, we can see that the algorithms do not converge to the same values of log likelihood. So this is a sign that it does not work well. And this is confirmed looking also at the samples, where here we compare the original coordinates to the sample coordinates. So when we would expect a straight line because we're comparing the original coordinates to the infer coordinates. So when we initialize the ground truth, we see that it works. But when we initialize randomly our samplers, we can see that they don't give the straight line we're looking for. And so one reason for that is the large amount of local maxima I was talking earlier. But also another problem is that the S1 model is actually not identifiable. And this is because there are symmetries in the model that we cannot resolve. So first, there are symmetries on the circle because we can rotate around the vertices, or we can flip around also the angles. And these symmetries preserve the distances. And since the likelihood depends only on the distances, we cannot distinguish these different embeddings. And furthermore, there are also symmetries that may come from the graph. So we have sometimes in graphs transformations we call automorphisms, where we relabel vertices and preserve the edges. And what happens in these cases is that we can exchange the positions of the vertices in the posterior and obtain again the same graphs. So this also means that it's hard to compare embeddings together, and we have to align them using these symmetries. And we have to sample our problem as best as we can while there are those symmetries going around. So what we realized in that problem is that the edges are local, and this has some very specific consequences. So here, what we realized is that we can cluster the vertices in the embedding together and move them as one entity. And so it's a kind of a coarse-grained approach where the connections between the vertices and the clusters should be the same in the graph since they are moved together at the same time. While there shouldn't be much connections in between clusters because they are quite far apart. And so here, for example, what we could do is pick the cluster here on the left and move it down, exchange it with the one which is down there. And so what we decided to do in our algorithm, in our sampling algorithm, is add those kinds of transformations which are inspired by the symmetries in the space. So first, we have what we call the flip transformation, where we pick a cluster and just mirror its image. And this targets the reflection symmetry I was talking about. And for the rotational symmetries, what we use are the translate transformation, where we pick one cluster and move it next to another. And we also have the exchange symmetry, where we pick two clusters and exchange their relative positions. And perhaps surprisingly, to our great surprise, only adding this to our random walk did wonders. So here we have what we call a BIGUE algorithm. It's simply a random walk to which we added these kinds of moves, but we can see that the convergence is much, much, much faster to the stationary state. And what we can see is that the oscillations around the log likelihood are very similar when we compare the two different initializations. And this is also confirmed when we look at the actual samples we get, where we see that the distributions look very, very similar. So now that we have an algorithm that works to sample our posterior, we can look at the properties of this posterior distribution. So we first looked at the error bars we get for the positions. So this is, again, a synthetic graph. So we know actually the ground truth in this case. And here we compare, so in blue, we have our posterior sample. In green, we have a maximum likelihood estimator, which is in green. And we can see that our error bars cover the actual maximum likelihood that was estimated. So both estimator are kind of coherent in some way. And this is the case for theta, but also for the other parameters where the degrees, the kappas are pretty similar. And the distribution of beta is also quite close to the Mercator value. Now, what's maybe more interesting to look at is what are the different properties of the graph when we use these embeddings to generate new graphs. So we can see that the distribution of some very basic properties, such as the density in the clustering, are quite different when we compare the posterior sample and Mercator. And this is not obvious when we look at the actual parameters of our model. And furthermore, when we look at properties that are obtained from the geometry, so here, if you remember earlier, I was talking about the greedy routing algorithm. And these greedy paths may not succeed in some cases. So this property here is the proportion of paths that actually succeed in our embedding. We can see that Mercator kind of overfits in some sense, where it finds very, very good paths, but it actually performs better than the ground truth of the model, which may seem a little weird. So now we done all of that for synthetic graphs, but what about empirical graphs? So we also compared the two approaches on various empirical graphs. And we can see that for the most part, the properties are quite similar, but the error bars for our posterior sample are quite a little bit larger. And this is because simply we consider a larger variety of embeddings. But I think what is interesting is in the last column, this is another geometric property that we compute from the embeddings. And we can see it doesn't really matter what that is exactly, but it measures how hierarchical our embedding is. And we can see that Mercator, as for the greedy routing, kind of overestimates how hierarchical our graph is. So the last thing we wanted to check is whether, so are there multiple good embeddings sometimes? And the answer is yes. And what we did to see that is again create a synthetic graph where here we have two ground truth for one vertex. So what I mean is that we have a fixed embedding, but there's one vertex in that embedding that has two positions. And so what that does is that when we generate a graph with the model, each edge might use one or the other position. So what it effectively does is that this vertex may connect to some vertices on top of the circle and some vertex at the bottom of the circle. And so it has sort of a conflicting position. And when we look at the marginal posterior distributions, we clearly see that there are two modes for the angular position. And these are not the actual vertices that were moved. So it was pretty interesting to see that. So this is the kind of thing that maximum likelihood cannot give us easily. Okay, so this is joint work that I did with my advisors, Antoine Allard and Jean-Gabriel Young. And so what we, in summary, what we saw today is that vertex embeddings are not identifiable because of the symmetries, both in the graph and in the space. And so to compare embeddings together, we have to align them. And what we saw is that the locality of the edges allow us to coarse grain this embedding using clusters. And using these clusters, we were able to find MC-MC algorithm, so a sampling algorithm for our Bayesian model, which can find error bars and identify multiple good embeddings for a graph. So if you want more information about the paper, more technical details, you can find this paper here, which is on arXiv and will be very soon in communication physics. Great, thank you. So is there any question? Are there any questions?
Thank you for reading this talk.
Thanks.
Let me see if I understood the main point. So the BIGUE is an additional set of iteration steps you take in your Monte Carlo.
Yeah.
Is that right?
Yeah.
You're basically adding those with some probabilities.
Exactly.
You can talk about probabilities, but they're related to Professor Hastings.
Yeah.
Okay. Then using that, you get your Mercator, which is the proofed embedding there.
Yeah, Mercator is a maximum likelihood, so it's a kind of separate from. Yeah. Yeah. Exactly.
So yeah, maybe tell us how these things get in practice.
Yeah, this is a pretty difficult thing to do. So what we did is that we, so to identify what are the clusters in our circle, we picked a threshold for which of the angular separation. And if the vertices are below this threshold of distance, it means that they are in the same cluster. And if they're above this threshold, they are outside. And since this threshold is not universal, what we did is in our Metropolis Hastings algorithm, we sample this threshold too. When we sample, yeah. So, and this makes things really hard mathematically because we need to marginalize over a bunch of things. But yeah, so we can have like many versions of clusters for the same embedding when we actually sample.
Well, I actually had a follow-up question on that. Just like I guess in theory, you could track over the course of the Markov chain what the clusters actually are.
Right.
And you find that there's like some interesting structure in that. Just like
That is a good question. We haven't looked into that actually, but there's probably when you start from a random point, the clusters don't really make sense. But I guess when you are in the stationary state, at some point you get some cluster that makes sense. But that's right. That's something we didn't look at, but could be interesting, right?
And then when you say the translation step,
yep,
you're kind of squishing the other.
Yeah, so you kind of moving this one there, and you like fill the gap, like you move this downwards.
I think it's precise. Is there any
No, it's precise. We find exactly the midpoint between the two vertices and like separate it like that. Yeah.
And don't you have to assign some probability to, let's say there are three options here.
Yeah.
How do you do that?
So I think it's 40% of the time we perform a random walk, and the 60% of the time we do these transformation and we pick them uniformly, one of the three. Yeah, simple as that. Yeah. Maybe we could try to fine tune the probabilities. It's not really something we look at. Yeah.
It's very vague, but as long as you get a chain that makes it well enough and you're willing to wait it, should be okay.
Yeah, exactly. Right. Right. And also in the paper, we computed some more. So this is kind of hand wavy, and we cannot actually like, I mean, these are some ways to see if it mixes well, but we can compute also some actual properties of the Markov chain, which we did in the paper. So we can compute the effective sample size. We can compute the potential scale reduction factor, the R hat. So we computed all of that, and this is all consistent. Our algorithm performs much better than all of that, all the others. Also, the autocorrelation is better for our algorithm, which is kind of surprising. It seemed like HMC should have worked better in terms of autocorrelation, but we found that it doesn't actually. This may be because the gradient is really hard because of the local maxima everywhere, and so the gradient is not really useful. I think maybe in that case.
When you say that the power law prior for kappas doesn't work well, what does it mean to not work as well?
Yeah, it's in the sense that when we look at these kinds of figures, the kappa didn't always match well with the degrees, at least for empirical networks. And I guess we could have tried to play a little bit more with the prior. But yeah, so we tried to use like a sort of universal prior, which in Bayesian inference doesn't really make sense. But I'm sure there's a way to make it work also with the power law. It's just that, yeah, we just found in practice it worked easier with the Cauchy distribution. But it shouldn't matter too much, I think.
Follow up on that one.
Yeah, of course.
Cauchy is a power law, and it's a -2 power law. Is that right? So the Rand's distribution, Cauchy distribution, it's over one.
That is a good question. Yeah.
So I guess you'd be some other power law that with a different exponent wasn't working as well.
Yeah, that might be right. I don't remember. That's possible.
Or maybe I'm just
No, it's possible because it's 1 over the 1 plus s squared, x squared, or something like that. So it makes sense. Yeah. So yeah, it is actually very close to a power law. Right. I think you're right. Yeah.
I'll just keep going.
Yeah.
So it's about these clumps that you're choosing. So you said you're sampling thresholds of right?
Of f theta. Yeah.
Is there anything that like potentially community structure? I guess this is a bit very closely related, but just like community structure per se as
yeah, it's a really good question, and that's something actually we've been asked a few times. Is that it seems like there shouldn't be on average a community structure in that, because we actually put a uniform prior on the angle, right? So it shouldn't be, but it turns out that the random fluctuations around this process is enough to work. And we actually, I mean, I didn't show it, but we tested our algorithm on a larger graph. So this was a really small graph I talked about earlier. And we can see that it still works really well. And this is with a random initialization. So like it still works very, very well. And we can see that in the ground truth, we don't have like we don't really see a cluster structure, but it's still, our algorithm still works. It still kind of untangles the order of vertices on the circle. That's how I kind of see it. It's still useful to kind of move chunks of the embedding around.
No, please. No, go ahead. No, please.
No.
Oh yeah, the graph morphisms. Did you find any idea with those?
No. Well, so what? It's a great question. Yes. So I think that if we were able to use automorphisms in the sampling, that would be helpful, for sure. So what we did actually, well, we did kind of consider them in the sense that when we aligned the embeddings together, we use an algorithm to just enumerate all of the automorphisms, and we optimized over that. So we did consider them, but not in the sampling part, because in some way I think it doesn't scale very well. So we're trying to avoid going that direction. But if there's a good algorithm that at least works approximately for the automorphism, I think that'd be pretty useful. And I also seen a paper, I don't remember by who, but they were talking about approximate automorphisms. And I think that also makes sense in that scenario where there could be like one or two edges that change when you relabel your vertices, but in the embedding, it doesn't really matter. So I think those could be helpful too.
I guess what you're telling us is the space symmetries.
Yeah. Yeah, it looked to be. Yeah, I think so. And I noticed that on larger graphs, I mean, we didn't work with very large graphs because it was difficult, but in a computational perspective, but it seemed like the larger graphs had less automorphism. And I think it makes sense that in general, if you don't have like a lot of symmetries in the graph structure, you don't have a lot of automorphisms. So I think it might not be that much of a problem for large graphs, but yeah, that I'm not totally sure. Yeah.
Follow up on that. How large can I go with that algorithm?
Very good question. So that's why I tried on 100 vertices. It takes quite some time to do this embedding. And the reason is not necessarily because of the n-squared likelihood, but more so about the actual autocorrelation that we get in the sample, which does not scale linearly with the number of vertices. So you need more sampling steps to get the same power of like estimation in Monte Carlo. Exactly, right. And so that's really a problem. So this is like not actually a lag of 10. This is a lag of like, I think 10,000, because there was already something in there. So it requires like approximately 10 times more thinning than for the 30 vertices graph. So it's a lot worse in that scenario. But I think there are many ways we can improve that. Like for sure, I'm sure there's a way to make HMC work. I'm sure there's a way to make it work instead of our a naive random walk. Maybe we need to fine tune it in some way. We didn't look too much into that because it worked well with the simple random walk. But I think that if we can mix HMC with our kind of clusters, I think that would work better for sure. Yeah. Oh. Hello.
We have a question in chat. So if I could maybe just.
Oh, all right.
So,
Nick, would you like to unmute yourself and ask a question?
Sure. Can you hear me?
No. So
computer is kind of freaking out. Sorry, my computer is kind of freaking out, but I still can answer the question.
Well, can you hear me speak or not?
Like this?
And then, no,
really close. And then
Okay. All right. Hi.
Hey, can you hear me?
Yeah, a little bit.
A little bit is probably not sufficient.
Yeah, I can't hear real well.
Nick, maybe can you just put it in the chat and then Eric will.
Yeah, I think it's going to be easier.
I did in fact put it.
Yeah, so,
It's in the chat
the
already.
question is, I was at a talk the other day on Bayesian spatial embedding, which was also concerned with correcting rotations, reflections, etc. The audience's main concern was whether there were any proofs or guarantees. So at the same time, we have here for basic or Hamiltonian MCMC. That these posteriors converge on the true parameter distributions. The paper fixed things after the fact on the parameter chain. Are there any formal guarantees that this approach works?
Yeah, we didn't check in the formal guarantees. One thing we did do that I didn't talk about is that we fixed one vertex in the embedding to to help avoiding the rotational symmetry. So there's a kind of anchor point somewhere where we can move around the other vertices. And also we restricted another vertex in the top half of the circle to avoid as much as possible the reflections. But we didn't look too much into the, I would say it's more of a numerical perspective on this sampling approach. And we saw that in practice, it seemed to work pretty well, but we didn't check into the actual proof of convergence and all of that.
Awesome. Yeah. So we've got another question in the chat, which is, I think it's a question about model selection, which is, does this approach lead to any sense in which you can get better generative models for networks?
That's a good question. Does it lead to better? I think there's probably a way to write a sampler to do model selection for sure. It might be quite difficult to do in practice. I don't think this work specifically helps for that, but I think it's a step towards these kinds of things. Yes.
Awesome. Any other questions online or in person?
What's next with this?
What's next?
Yeah.
Okay, so well, first, one thing we could do is try to
Yeah. I'm sorry.
So one thing we could try to do is embed in higher dimensions. That's for sure. And I think this may or may not help for the mixing. That we will see. But one idea we had is that maybe when you sample in higher dimensions, so on the circle, you cannot move like vertices. You need to move vertex like past each other, but you don't have a dimension to go around. So maybe increasing the dimension can help in that regard. And so kind of smoothen out a little bit the posterior. So that's one thing. But that would probably require using Hamiltonian Monte Carlo, I think, because getting even more dimension for a random walk, I don't think it's, I think it's going to be pretty hard to get good convergence. So that's one thing. And the other thing, I think, just adding the Hamiltonian Monte Carlo to our sampler is definitely something to look forward to. Yeah.
Right. Well, thanks everyone. Wonderful talk, Simone. Let's thank Simone once again.